Okay, welcome everybody to the live review session for bonding. I'm Mr. P, and I am a chem teacher from William Floyd High School. Before we begin, we are aware there's a problem with the previous video on solutions. They are working on fixing that problem, and a working link will be posted at some point later on today. So you can check back later, and we guarantee that will be up for you. Okay, so let's go through bonding. I have some embedded questions, and at the end, I pulled some questions from the January 2016 Regents exam, and we can go through those questions together. And if we have time at the end, I can kind of look at your chats and see any questions that we haven't answered yet. Okay, so what is a bond? A bond is a force of attraction that holds one atom to another in a compound. Why do atoms actually bond in the first place? Remember that atoms want to bond together to get that stable octet. They want 8 valence electrons, with the exception of hydrogen, because that can only have 2. We call that a stable duet. Recall that forming a bond, so when a bond is formed, energy is released. That's an exothermic process, and it's released spontaneously. And the result is the formation of a stable compound. So for example, if we take pure sodium and we take chlorine gas, they come together, they release a lot of energy, and the result we get is table salt. Breaking a bond, when we break a bond, energy is absorbed. That's an endothermic process. And because of that, the stability decreases. So a good example would be ripping apart 2 atoms requires energy. And an easy way to remember that is BARF. So breaking bonds absorbs energy, and releasing formed. So let's stop and think and look at a practice question. So which statement best describes the energy change as bonds are formed and broken in this reaction? So we had the reaction between hydrogen and chlorine making 2 moles of HCl. Okay, so we see we have H2 and Cl2. They're coming together, they're forming a bond. So if you think of your BARF here, if we're forming a bond, we get a release of energy. So we're looking for a release of energy, so we can get rid of choice B, and we can get rid of, actually that's it for the release. So now we know we are forming a bond, so we're forming and we are releasing energy. So choice A. What I want to do now is go through the different types of bonds that we have. The 3 main types we have: ionic, covalent, and of course metallic. So first and foremost, the ionic bond occurs between metals and nonmetals. So metals are on the left-hand side of the periodic table, and we have our nonmetals on the right-hand side of that staircase. And for ionic bonds, there is a transfer of electrons from the less electronegative, which is the metal, to the more electronegative, which is the nonmetal. And when we do that, we form a bond and we become stable. The properties of our ionic compounds. They're typically hard, crystalline in structure. They have a high melting and boiling point, and that's due to that strong electrostatic attraction. They tend to be soluble in water, and of course they can conduct electricity only when they are in solution, so only when we see that they are aqueous. And the reason why is because when they go into solution, they're going to break apart into ions. We have these charged particles floating around, and whenever we have movement of charges, we can get conduction of electricity. And we can see that here. So pure water, H2O, covalent, does not conduct. And also our ionic compounds in the solid form do not conduct. But when we put our ionic compounds in solution, they will conduct. And we call these things electrolytes. So let's stop and think for a moment. Which formula represents an ionic compound, an electrolyte? Okay, so choice A is going to be covalent. We have nonmetal and nonmetal. Choice B is also covalent, nonmetal and nonmetal. Choice C, sometimes we can get fooled with this. We see the OH, we may think a base, and a base is an electrolyte. But this is not a base. This is an organic compound. This is called an alcohol. And therefore, this is not ionic. So choice D is our answer. It's ionic because calcium is a metal and chlorine is a nonmetal. Okay, now let's look at covalent bonds. Covalent bonds occur between nonmetals and nonmetals. So both elements are on the right-hand side of the staircase on the periodic table. In covalent bonds, instead of a transfer of electrons like ionic, we have a sharing of electrons to obtain a full valence shell and become stable. And they form molecular substances. So when we see the word molecular, that's going to be interchangeable with covalent on the Regents exam. And the trick to remember, sharing is caring. So for covalent, there's a sharing of electrons. So what are our properties of covalent compounds? Well, they are soft. They have low melting and boiling points, and that's due to their weak intermolecular forces, those forces of attraction between molecules. And they do not conduct electricity due to lack of charged particles or ions in solution. And lastly, we have the metallic bond. A metallic bond occurs between metal atoms of the same element. So we can't get a metal bonding with a different type of metal. The metallic bond is what holds all of the atoms of one particular metal together. So for example, if I can zoom in on this gold ring, what's holding all the atoms of gold together? Metallic bonds. Metals tend to have high melting point and high boiling point because of those strong bonds. So they're always capable of conducting electricity because, as you can see here, we have mobile electrons. And the reason why is that metals have a very low electronegativity and they have a very low ionization energy. So these electrons aren't being really pulled in very tightly close to the nucleus, and therefore they have the ability to kind of float around. And that movement of electrons or charges allow us to conduct electricity. Let's look at an example. What type of bond is created in the following? So we have A, B, C, and D, all these three things. So for each one, take a moment and try to identify what type of bond is occurring. Okay, so for the first one, we have KBr. K is potassium, that's a metal. Br is bromine, a nonmetal. So a metal and a nonmetal is going to give us an ionic bond. Hi, don't forget that hydrogen, even though it's on the left-hand side of the periodic table, it is a nonmetal. So nonmetal and nonmetal, B is going to be covalent. For C, we have nitrogen and oxygen, both nonmetals. That's also covalent. And for D here, we have lithium, which is on the left-hand side of the periodic table. That's a metal. And chlorine is a nonmetal. And we know metal and nonmetal will make an ionic bond. Let's try another question. A solid substance is an excellent conductor of electricity. The chemical bonds in this substance are most likely, and I'll give you a minute, look through the question, and then we'll go over it. Okay, so right off the bat, we can get rid of choice A and choice B. And the reason why, it says this substance is an excellent conductor in the solid form. And ionic compounds do not conduct in the solid form. So choice A and choice B are out. So we're left with choice C and D because we know metallic will conduct in all phases. Okay, why are they conducting? Well, if you recall in the previous slide, those valence electrons are delocalized. They are mobile, or a sea of mobile electrons. So the correct answer is choice D. It's a metallic substance because the valence electrons are mobile, meaning moving. And let's try another question. What type of bonding exists in BaCl2? And then question 2, describe in terms of valence electrons how the chemical bond forms in BaCl2. Okay, so we have barium chloride. Barium is a metal, chlorine is a nonmetal, so this is a ionic bond. And in terms of valence electrons, how the chemical bond forms, Well, we know that in ionic bonds, there is a transfer of electrons. So in terms of valence electrons, there is a transfer of valence electrons from barium to chlorine. Don't forget about table E, our polyatomic ions. These contain, when we have a substance that has a polyatomic ion, it contains both ionic and covalent bonds. The atoms in a polyatomic ion are held together by covalent bonds, and they form an ionic substance or ionic compound because ionic compounds are formed by ions coming together. So for example, NH4Cl, ammonium ion, which is NH4+, these bonds are covalent, but the attraction between this ion and this ion is going to be an ionic attraction. And this is our table E, as you see here. And there was our ammonium ion. So whenever you see a polyatomic ion, we know it contains both types of bonds. So which compound contains both covalent and ionic bonds? So take a moment, open up table E in your reference table, and we'll go over this in a second. Okay, so the correct answer is going to be choice D, which is barium sulfate. And the reason why is the SO4 is on table E. So what's holding the sulfur and the oxygen together? That is a covalent bond. And then barium and the sulfate ion come together to form an ionic substance. Okay, now that we discussed the main types of substances we have and the main types of bonds, we have to talk about bond polarity. So this occurs for covalent substances. So first thing we ever do is determine if a substance is ionic or covalent. If it's ionic, then we're done. If it's covalent, then we have to determine if it is going to be nonpolar or polar. So is it sharing the electrons equally, nonpolar, or is it sharing them unequally, polar? So the nonpolar covalent bond is equal sharing of electrons. So if you think of a game of tug of war, and these are our valence electrons, then both atoms kind of have the same strength or same pull. And that pull is the electronegativity. So to categorize a nonpolar covalent bond, we look up on table S the electronegativity values of each atom. And the electronegativity difference, the END, has to fall between 0 and 0.4. So it's essentially showing that they have essentially the same strength of attraction, and therefore sharing those electrons equally. It usually occurs between atoms that are the same, so diatomic elements, for example, because they have equal electronegativity difference. Oh, sorry, they have equal electronegativity, so the END would be 0. Another common example would be carbon and hydrogen. If you do the electronegativity difference between carbon and hydrogen, we notice that it's 0.4, right on the cusp, but it's still a nonpolar covalent bond. A polar covalent bond occurs when there's unequal sharing of electrons. So one atom is stronger, has a higher electronegativity than the other. And the electronegativity difference between those two atoms is going to be greater than 0.4. Now I put 0.5 to 1.7. This is kind of an arbitrary ending. The reality is we don't really care too much about this because once we've identified it as being covalent, we know it's covalent. And if it is greater than 0.4, it has to be polar. Because of the unequal sharing, we get a dipole setup. And what does that mean? It means that we have two poles, and one end becomes partially positive and one end becomes partially negative. And a good example would be HF. So fluorine is much more electronegative. So you can see that it is very, very electron rich. There's a lot of electrons around the fluorine. And then the hydrogen then becomes electron poor. This becomes slightly positive and the fluorine becomes slightly negative, as we can see here in this diagram here. So if we compare them all, if we have equal sharing of electrons, that's a nonpolar covalent bond. If we have unequal sharing of electrons, that means someone is more electronegative than the other, we have a polar covalent bond, and we see you have partial charges set up. And then eventually when they become so polarized, one is way more electronegative than the other, we get an ionic substance. And we get two complete different ions with different charges. So let's recap. How do you determine the type of bond? First thing, determine if it's ionic or covalent. If it's ionic, then we know it's metal, nonmetal, and we're done. If it's covalent, which is nonmetal and nonmetal, then we look up the electronegativity values and determine the electronegativity difference between the two nonmetal atoms. If the difference is greater than 0.4, it's polar. If it's less than 0.4, it's nonpolar. So let's look at some examples here. For each one, try to determine if it's ionic or covalent, and if it's covalent, is it polar or nonpolar? So I'm going to give you, let's say, 30 seconds to look through these, and then we'll go over them. Okay, for the first one we have NaS. So the bond between Na and S, we have a metal and a nonmetal, is going to be ionic. For the next one, we have CBr. And what we can do is I can pull up, let's see if we can pull up table S. Just bear with me. Let's see if I can get this up on the screen for you. All right, I don't know if it's going to project on here, so give it one more shot. If not, I'll just read it off for you. Okay, it's not going to work, so I'll just read off the values. So if you have your table S in front of you, you locate, well, first determine that this is nonmetal and nonmetal, so it's going to be covalent. And now we want to figure out, is it polar and nonpolar? So we look up carbon, and we see that carbon is 2.6 on table S for a electronegativity value. And then we look up bromine, and we see that bromine is 3.0. So 3.0 minus 2.6, a difference of 0.4. So this would be a nonpolar covalent bond. The next example we have nonmetal. So this is going to be covalent. Since they're both the same, the electronegativity difference is going to be 0. So for this would be a nonpolar covalent bond. For the next example, we have H and we have O. Both of those are nonmetal, so it's covalent. We look up hydrogen, and it has a value of 2.2 for electronegativity. And then we look up oxygen, and oxygen is going to be 3.4. So 3.4 minus 2.2, that is greater than 0.4. So this is going to be a polar covalent bond. For the next one, we have diatomic fluorine. So since they're both the same atom, or both same element, the electronegativity difference is going to be 0. So that's going to be a nonpolar covalent bond. And for the last one, we have Ko. This is a metal, potassium, and oxygen. So this would be metal, nonmetal. This would be an ionic bond. Okay, let's stop and think for a moment. The electrons in a bond between two iodine atoms are shared. I'll give you a second, read through the question, and then we'll go over it. Okay, so we have diatomic iodine. So they are two of the same atoms. They're sharing electrons. If they're sharing electrons, it's going to be covalent, but we can tell that because they're both nonmetals. And since they are both the same atom, the electronegativity difference is going to be 0, which means they're sharing them equally. So choice A and C are out. And if they're sharing them equally, it has to be nonpolar, so the answer is choice D. Okay, our next part, we're going to go through drawing Lewis dot diagrams for both ionic and covalent. So let's first focus on the ionic compounds. If you recall, drawing the dot diagram for positive ions, which are metals, we have the symbol of the metal followed by or inside brackets with the charge of that metal on the outside on the upper right hand corner. There were no dots representing that there was a loss of electrons. And then for the negative ions, recall that for nonmetals that we have, again, the symbol, we have 8 dots representing the full valence shell. And then we have our brackets and then the charge again on the upper right-hand corner outside the brackets. So for an ionic compound, we're essentially just putting these together. So let's see an example. If you want to draw a dot diagram for NaCl, we have the sodium ion, and we place that next to the chloride ion. Again, notice the metal has no dots, brackets and charge. Non-metal has 8 dots, brackets and charge. Calcium chloride, we have 1 calcium, we have 2 chlorine. So we put the calcium in the center, and then we put our 2 chlorines on the outside. And we could always verify that we did this correctly if you looked at the total charge must equal 0. So we have 1 negative, and 1 negative gives me 2 negative charges, and then 2 positive charges gives me a neutral compound. Okay, let's take a moment and try a practice problem. Let's draw the dot diagram for barium sulfide. So the first thing you would do is say, okay, barium is a metal, sulfur is a nonmetal, so metal, nonmetal, we know it's ionic, and we know that we're going to draw this ionically. Okay, so we should have something that looks like this. So we have our metal, brackets, and our charge. Again, no dots around the barium symbol. And then for the sulfur, we have 8 dots, brackets, and our charge. Notice that the charges will equal 0, so +2 and -2 will give us a neutral compound. Let's try another one. Let's draw the dot diagram for LiS2, or lithium sulfide. Again, take a moment, draw that out, and then we'll go over it. Okay, so as before, we're going to put the metal in the center, and we're going to put our 2 sulfurs on the outside. In reality, on the Regents, if you put both sulfurs together, you would still get credit for the answer. But the reason why we do it this way is that we want the negative being attracted to the positive, and then the positive being attracted to the negative. That's why we write it this way. Always verify that you have the right charge for the ion. If you wrote for example, if you wrote -1 by accident, then the whole thing is wrong. So always go back and double check that you have the correct charge. So lithium is +1, and then for sulfur, which is going to be our negative charge, which is going to be -2. Okay, how do we draw dot diagrams for covalent compounds? Now these are a little bit more involved. For covalent compounds, every teacher kind of has their own way of teaching this. So I'm going to show you how I do it. But if you're more comfortable with the way your teacher taught you, then feel free to use that method. The end result is we're going to get the same answer. Okay, so if you're given an example to draw, for example, the dot diagram for water, H2O. For any covalent compound, first thing that you want to do is you want to add up the total number of valence electrons. So oxygen is going to be 6 valence electrons, hydrogen is 1, and since there are 2 of them, 1 times 2 gives me 2, plus 6 gives me 8. So I have 8 valence electrons to deal with. Then what I want to do is, if I have a unique atom, one that's not like the others, in this case oxygen, I put that in the center. And then I put the other atoms on the outside. And I try to keep things kind of very linear. So I work across first, and then if you have more, you can go up and down. Now I know I have 8 valence electrons, so what I like to do and tell my students is I give the central atom 8 electrons first to make sure that this is bonding with everyone that it can bond with. And then if I have extra electrons, I dish them out evenly to the other atoms that are attached. So once I dished out my 8, if I have more, I dish them out. In this case, I don't. I only had 8 to give out. So now I check to see if everyone has a full valence shell. So we know that oxygen needs 8, and we know it has 8. And then hydrogen, that's that unique case we talked about. Hydrogen only has 1 shell, and therefore it can only have a maximum of 2 valence electrons. So in this case, it's going to have 2, as we can see here, and of course this one as well. So everyone has a full valence shell. That is a completed dot diagram. Now you can draw it linear like this. If you remember that water is actually going to form a bent shape, you can also draw it in a bent fashion. So kind of move this hydrogen down here. It doesn't matter. As long as you have 2 hydrogens and then you have 2 lone pair electrons, we know it's a correct dot diagram. Okay, let's try another example. Now I want to draw a diatomic fluorine. So again, add up the total number of valence electrons. So I have 7 for each fluorine, gives me 14. In this case, I don't have a unique atom. They're both the same. So I just pick one to be my central atom, and I give it 8 electrons. So let's say I pick the first one on the left-hand side. I give it 8. And then I dish out the rest. So I pair them up, 2, 4, 6. Gives me a total of 14 electrons. Always count them up and make sure that everyone has a full valence shell. So we know that this fluorine has 8 and this fluorine has 8. Now you can draw them 2 different ways. These are both correct or acceptable answers. For every pair or bonded pair of electrons, we can remove them and draw a bonding line, as I did here. So either one is correct. You just can't do both. I can't have a bonding line and then also have the dots for the electrons. Okay, let's try some more practice. Let's draw the dot diagram for HBr. So I'm going to give you a moment to draw that out, and then we'll go over it. Okay, for HBr, you could end up with either the one on the left, or if you'd like to use the bonding lines, we can have the one on the right. Remember that hydrogen can't have more than 2 valence electrons. So don't dish out 8 electrons around the hydrogen. That can't exist. So we dish out the 8 around the bromine, and therefore now hydrogen has a stable duet and bromine has a stable octet. And if you don't like the 2 dots for the bond, you can use the bonding line. All right, let's stop and think for a second. Let's draw the dot diagram for methane, CH4, and then tell me what is the total number of shared pairs of electrons in the compound. Okay, so as I said, I like to do is I put this unique atom in the center. So I'm going to put my carbon in the center, and then I'm going to have my 4 hydrogens around on the outside of the carbon. I determine the total number of valence electrons. So a carbon has 4, hydrogen has 1, and there are 4 of them. So 4 plus 4 gives me 8. And I get either this version of the dot diagram with my 8 dots around carbon, Or if you want to use the bonding lines, you can do that and you get this version here. Now the question says, what is the total number of shared pairs of electrons in the compound? Total number. So we have each line represents a bonded pair or a shared pair. So we have 1, 2, 3, 4. We have 4 shared pairs of electrons. And another stop and think. Let's draw the dot diagram for diatomic chlorine. And then once we're done with that, what is the total number of electrons shared between the 2 chlorine atoms? So I'll give you a moment to work that out, and then we'll go over it. Okay, since it's a diatomic element, I'm going to put both chlorines in a linear fashion straight across. Determine the total number of valence electrons. So we have 7 valence electrons in each chlorine. So 7 and 7 gives me 14. And you should get either the left-hand side or the right-hand side, again, depending on if you want to use the bonding lines. Always make sure everyone has a full valence shell. So we have 8 for this chlorine, and we have 8 for this chlorine. And we know we have a stable compound. What happens then if we give out all our valence electrons and we don't have a stable octet for everyone? So we don't have a full valence shell for all our atoms. That's when we have multiple bonds being used. And we get a double bond or a triple bond. So the most common example I would say would be carbon dioxide. So when we draw a dot diagram for carbon dioxide, what happens is we have lone pair electrons on that central carbon that aren't initially being used. So what we do is we can shift them down into the bonding site and make them bonding electrons. And therefore now carbon has 8 valence electrons. Oxygen is going to have 8, and so is this oxygen. So we end up with what's on the left-hand side here. This is actually a misprint here if you see that. So just be aware that these electrons were being moved so we can get rid of this right here. I apologize for that. So the result really is going to look like this here, where we have 2, 4, 6, 8 electrons for this oxygen, 2, 4, 6, 8 valence electrons for our carbon, and then 2, 4, 6, 8 valence electrons for this oxygen. What are some other examples of multiple bonds that you need to know? You should know carbon dioxide. That's probably the most common one. Other ones that we get are oxygen, which is going to have a double bond, and nitrogen, which is going to end up with a triple bond. So make sure you know how to draw these and you're aware of their bond formation. And again, recall how many electrons that are shared in a single, double, and triple bond. They will interchange questions. They may say how many total electrons or how many shared pair of electrons. So watch the wording. So for a single bond, we have 2 total electrons or 1 shared pair, as we see here in the single bond between hydrogen and hydrogen. A double bond is 2 pairs of electrons or 4 total electrons, as we can see here. So we have 1 pair, 2 pair, or we have 1, 2, 3, 4 total. And then triple bond, 3 shared pair or 6 total electrons. So we have 1, 2, 3 shared pairs or 2, 4, 6 total shared electrons. So just watch that wording on the Regents exam. Okay, so we talked about bond polarity. Now we're going to focus on molecular polarity. Recall that we have 2 types of electrons. We have the bonding pair of electrons. Those are going to be forming bonds. Those are in between our atoms. And then we have the lone pair electrons. These are the non-bonding electrons that are not bonded to other atoms. So how do you determine if a molecule is polar? We know how to determine if a bond is polar. That's the electronegativity difference. But how do we determine if the molecule is polar? That involves symmetry. So for a polar molecule, there is a symmetrical distribution of charge. Also, if the central atom has lone pair electrons on it, then it's automatically polar. That's going to help you out for things like water, for example. Because if you draw out the water dot diagram, it may look very linear and it may look symmetrical. In reality, water is very polar and it's asymmetrical. And that's due to these lone pair electrons. So whenever you see lone pair electrons on the central atom, automatically the substance is polar. So polar molecules, symmetrical. Non-polar molecules are going to be, actually that's a misprint. My apologies. So we can fix that. So for polar molecules, it's going to be asymmetrical. So let's fix that right now. Okay, there we go. Sorry about that. So polar molecules, we have asymmetrical distribution of charge. So they're not symmetrical, like water, for example. And again, if we have those lone pair electrons, we know it's going to be polar. And then non-polar molecules are going to have symmetrical distribution of charge. There's a quick little acronym we can use, which is SNAP. So symmetrical non-polar, asymmetrical polar. Okay, so again, we'll recap that. So polar molecules, not symmetrical, asymmetrical, and then non-polar, symmetrical. What are the most common examples of polar molecules? Well, most common example we have is going to be water. And you can see here, as I was discussing before, is that water is not a linear shape. It's actually a bent shape. We know it's polar automatically from those lone pair electrons on that central atom. That tells us it's going to be polar. Another common example is ammonia, NH3. NH3 again has the lone pair electrons, and this one you can tell right off the bat that it's not symmetrical, it's asymmetrical. When you draw water this way, we can tell it's asymmetrical, but we can't when we draw it in a linear fashion. And then examples like HF or HBr or HCl, these are also going to be asymmetrical in terms of our distribution of charge, and these are going to be polar. The most common examples of non-polar molecules are going to be things like methane, CH4, or really when there's one atom and then 4 identical atoms bonded to it. That's going to be a non-polar molecule, and that's that tetrahedral shape that we have here. It's because it's symmetrical, so the charge distribution is going to be symmetrical. Any diatomic, any of the 7 diatomics that we have, so I teach the Brinkelhoff, to remember our diatomic elements. So these are always going to be nonpolar because they're going to be symmetrical in terms of their distribution of charge. And another common example, carbon dioxide, which looks like this. It's a linear shape, but it is symmetrical, and therefore it's going to be a nonpolar molecule. So here's a summary of our shapes and polarity. So if that central atom has just 1 or 2 bonds to it, it's going to give us a linear shape. Linear is the only shape that could either be one or the other. It could be polar if it's asymmetrical, or it could be nonpolar if it's symmetrical. If we have 2 bonded pairs and 2 lone pairs, or if we have any lone pairs, we know it's going to be polar, but 2 bonded pairs, 2 lone pairs, that's water. That gives us a bent shape. 3 bonded pairs and 1 lone pair, that's polar, again, because of the lone pair, and that's our pyramid shape, pyramidal. And if we have 4 bonded pairs and no lone pairs, that's nonpolar, and that's our tetrahedral. So going back to our examples, water, since we have lone pair electrons, and we have 2 of them, that's going to be our bent shape. Ammonia, NH3, has 1 lone pair electron, and we have 3 atoms attached to the nitrogen. That's polar, and that's going to give us our pyramidal shape. And HF, since we have just 1 bonded atom, that's going to be linear. And you can tell right from the fact that by looking at it, it's linear. For the nonpolar examples we had, CH4 I mentioned earlier, since we have 4 atoms around the central atom, that's going to be tetrahedral. Here we have 1 atom bonded to another, so that's going to be linear. And the same for carbon dioxide. All right, let's look at an example. Determine the molecular polarity and shape of CCl4. So if you draw out CCl4, it has a very, very similar shape as the CH4 we did earlier. We have carbon in the center, no lone pair electrons, and we have 4 atoms around that central carbon and bonded to it. That's going to be nonpolar because it's symmetrical in terms of the distribution of charge, and the shape is going to be tetrahedral. Tetra meaning 4, so 1, 2, 3, 4 things bonded. Let's try another example. Determine the molecular polarity and shape of H2S. So take a moment, draw out H2S, and tell me if it's polar or nonpolar, and also the shape. I'll give you a moment for that. Okay, so first thing you want to do, since it is covalent, we're going to put our unique atom in the center, which is the sulfur. The 2 hydrogens will be on either side of the sulfur. Count up the total number of valence electrons. I'm going to dish them out to the sulfur first. Make sure you have a full valence shell for the hydrogen and the sulfur, and you should get something that looks like this. And the way that I drew this out, at first you may want to say it's linear, but it is not. We have lone pair electrons on the central atom. So first and foremost, in terms of polarity, this is polar. And because we have 2 lone pair electrons, it's going to form that bent shape just like water. So it gives us something looking like this. And when you draw it in a bent shape, you can see that it's definitely not symmetrical. So it is polar due to the 2 pair of lone pair electrons, and it's the bent shape, again, just like water. Let's try another practice problem here. What is the shape and polarity of CBr4? CBr4. So I'll give you a moment. So you could draw this out and draw the dot diagram out, or you may have noticed, again, as I mentioned earlier, that when you have 1 atom and then it's bonded to 4 of the same atoms, just like CH4 and CCl4, then you should have caught on that this 4 indicates that it must be tetrahedral in shape, and because it's tetrahedral, it's going to be symmetrical and therefore nonpolar. So if you draw it out, you get the dot diagram looks like this. We have 1, 2, 3, 4 atoms around a central atom. That gives us our tetra, so tetrahedral. And because, again, it is symmetrical, it's going to be nonpolar. And one last stop and think question. Determine the shape and molecular polarity of NF3. Okay, so to draw NF3, you should get something like this. Once you draw it out, you notice that there's a lone pair of electrons on the central atom, just 1. That gives us our shape of the pyramids. We call it pyramidal shape. And since it's pyramidal and it's not symmetrical, it is going to be polar. So it's pyramidal is the shape, and the molecule is polar due to the fact that it has asymmetrical distribution of charge. Okay, the last topic we're going to cover is going to be the intermolecular forces of attraction between molecules. Once we're done with that, we'll go through some problems on the past January 2016 Regents exam. And if we have any time left, I will look at the live feed and see if I can address any questions that have come up. Okay, intermolecular forces, or IMFs for short, these are very weak forces of attraction that occur between neighboring molecules in a covalent compound. So recall that this attraction between an atom and another atom is called a bond. This is a covalent bond. The attraction between neighboring molecules, is weak, and that's called an intermolecular force. Intermolecular forces have an effect on the melting and boiling point. The stronger the intermolecular force, the more energy it requires to break that force or break that connection. And the more energy it requires, the higher the melting and higher the boiling point. So they often give questions on the Regents exam where they have a list of different molecules and either their melting or boiling point, and they'll say which one has the strongest intermolecular forces. You're looking for the highest melting and or boiling point. And the strongest of these weak intermolecular forces is going to be the hydrogen bonding. This occurs between hydrogen of one molecule and either fluorine, oxygen, or nitrogen in another. And I'm sure every teacher gives this little saying here: hydrogen bonding is fun. Helps you remember that it's hydrogen and then one of these other very electronegative elements. So if you have an example here like water, water has H here and it has the O here. And what actually happens is that it occurs, this hydrogen bonding with this intermolecular force of attraction occurs between hydrogen of one molecule and the oxygen of the other, because oxygen is very, very negative, because remember, this is a dipole. And then the hydrogen is positive, has a slight positive charge. So obviously we have opposites attract here, and we get this connection. And this is why, since it's a strong, weak intermolecular force, this is why water has a somewhat high melting and boiling point as compared to other covalent compounds. And also accounts for other unique properties of water, such as surface tension, etc. Here's another example, NH3. So remember, hydrogen bonding is fun. So here's the H and here's the N. And we can see that this hydrogen bonding is occurring between the N of one molecule and the H of the other. So let's stop and think for a second. Which would have a higher boiling point? N2 then, or NH3? And explain your answer. So we get a question like this on the Regents. First, determine which one has a stronger intermolecular force. So N2 is going to have the weakest. I don't know if your teacher taught you this, but this would be the dispersion force, or they may even mention van der Waals forces. This is a very, very weak intermolecular force holding neighboring diatomic nitrogen together. And then we have NH3. We know that NH3 has the N and the H. This is hydrogen bonding. So this is a stronger intermolecular force. Once you know that this is a stronger intermolecular force, it's going to have a higher boiling point. So in your explanation, you can say that NH3 has a stronger intermolecular force and therefore a higher boiling point. If you want to be specific, you could say it exhibits hydrogen bonding and therefore has a stronger intermolecular force, and as a result has a higher boiling point, if you want to get very elaborate in your answer. So we did have one question from the audience in our forum we had a few weeks back. They said, what are the steps to know whether something is polar or non-polar? And I did address this, but I want to just bring it back for that individual that asked that question. Also need to know, are they talking about bond polarity or are they talking about molecular polarity? So very, very quickly, the first thing you do is determine if the substance is covalent. That's non-metal, non-metal. If it's covalent, then we look and see in the wording, are they asking about bond polarity or molecular polarity? So look for those keywords, bond or molecule. If it's bond polarity, that's between atoms in the covalent compound. Remember, nonpolar is an electronegativity difference from table S of 0 to 0.4. And a polar covalent bond would be any electronegativity difference greater than 0.4. If they're talking about molecular polarity, that's the symmetry. If it's symmetrical distribution of charge, it's nonpolar. If it's asymmetrical, then it's going to be polar. Okay, so what I did is I pulled some problems from the January 2016 Regents, our most recent Regents exam, And there actually were quite a few short answer questions dealing with bonding. So we can go through these now. So the first one says, the Lewis electron dot diagrams for 3 substances are shown below. Diagram 1, 2, and 3. Describe, here's the in terms of, so describe in terms of valence electrons, how the chemical bonds form in the substance represented in diagram 1. So they're only talking about diagram 1 on this question. And again, in terms of valence electrons, how the chemical bonds form in the substance. So I'll give you a moment to think about that, and then we'll go over the answer. Okay, so looking at diagram 1, and we see we have potassium, which is a metal, and we have bromine nonmetal. You also may notice the fact that it's drawn using the Lewis dot diagram for ionic compound. So this is an ionic compound. Once we know it's ionic, in terms of valence electrons, how the chemical bonds form, they form by a transfer of electrons. Or you can be specific. You can say that potassium loses an electron and bromine gains an electron, if you want to be more specific. Or again, just a transfer of valence electrons. The next problem deals with the same diagram. So again, the Lewis electron dot diagrams for these 3 substances are here. In this one, looking at diagram 2. So it says, determine the total number of electrons in the bond between the nitrogen atom and the 3 hydrogen atoms represented in diagram 2. So determine the total number of electrons in the bonds between the nitrogen and hydrogen. Okay, so the total number of electrons is going to be 6. We have 2 shared between this hydrogen and nitrogen. We have 2 between the one on the right, and then 2 between the nitrogen and the hydrogen on the bottom. So a total of 3 shared electrons. And then up top, just as a reminder, these are unshared electrons. These are called lone pair electrons. Okay, next problem, also dealing with the same diagram. It says, explain in terms of distribution of charge why a molecule of the substance represented in diagram 3 here is nonpolar. So they're telling you it's nonpolar, and they want you to explain why in terms of distribution of charge. So first off, just a recap here. This is a tetrahedral shape because we have 4 atoms around a central atom. And we know this is going to be nonpolar because they're telling it's nonpolar. But they want to know in terms of that distribution of charge, why is it nonpolar? It's nonpolar because it has a symmetrical distribution of charge. This diagram here, diagram 2, is polar because it has an asymmetrical distribution of charge. It's asymmetrical, it's not symmetrical. Okay, also from this Regents exam, another question was, draw a Lewis electron dot diagram for a molecule of Br2. So I'll give you a second to draw that out. Okay, so first and foremost, I look at Br2. It's 2 nonmetals. That's going to be covalent. So I'm going to draw this using the covalent method. So there's no brackets. This is not ionic. And you should have either the one on the left with all dots, or if you like to replace the bonded pair of electrons with the bonding line, you have something like this. Either one is a correct answer. Okay, and then on to some of the multiple choice questions. Which compound contains both ionic and covalent bonds? So looking for one containing both ionic and covalent bonds. Okay, so the first choice we have is metal, nonmetal. This is ionic only. Choice 2, calcium is a metal, chlorine is a nonmetal, so metal, nonmetal. This is also only ionic. Choice 3, we have C, H, and Br. These are all nonmetals, so this is going to be only covalent. And then we have choice 4. Choice 4 has our metal, Na, so we could be thinking it's going to be ionic, but it actually contains both. The bond that is between carbon and nitrogen is actually covalent. Cn is actually coming from table E of our polyatomic ions. So this contains both an ionic bond and a covalent bond. So the ionic bond is between Na and Cn, and then the covalent bond is between the C and the N in the polyatomic ion. Okay, given the balance equation representing a reaction, we have H2, which is decomposing into H and H. What occurs during this reaction? So I'll give you a moment to read through the answers. Okay, so first off, we have a molecule here and we're breaking the bonds. We're breaking it apart. So we know bonds are being broken. So we can get rid of choice 1, which says bonds are formed, and choice 3, which says bonds are formed. So now we're left with choice 2 and choice 4. And you should do this for every question on the Regents exam. Always get rid of the 2 that off the bat don't make any sense. And now we have to figure out, is energy being absorbed or released? But when you want to break something, you have to put energy in. So that means it's going to absorb energy. So energy is being absorbed as bonds are being broken. That is choice 2. And remember the acronym BARF that we talked about in the beginning of this live stream. All right, so we finish up our questions. We have about a minute left or so. I am getting word that our previous video, which is the solution stream, has been fixed and a new link has been posted. So please check back for that if you're looking for any live review on solutions. I hope you enjoy all the rest of the videos. I watched a few so far and they've been great. If you have any questions, you can send them through the Remind chat and I will get back to those questions later on today.